architect of the data insights team. He's going to be speaking about some work he's been doing with Spark SQL. So a nice big hand for Santosh, please.
Hello? Can everyone hear me right?
Yes.
Back. Okay, thank you for coming into this Spark meetup at Concur. My name is Santosh Sahoo. I work for Concur as a principal architect, and today I'll be presenting this topic on breaking ETL barrier with Spark streaming. And this is one of the interesting experiments that we're doing with Spark streaming to solve one of our use cases. And I'm just wondering, how many of you have already worked with Spark or know Spark about Spark? Quite a bit. How many of you know about Spark streaming already? Okay, quite a few. So yeah, so the agenda of this presentation is primarily to talk about some of the business cases, and then followed by we'll have a demo showing you how a Spark streaming application works. And then I'll be doing some deep dive into Spark streaming architecture. And if you have any questions anytime, feel free to raise hands and ask questions. And also, I'll be presenting our architecture, how we are building our platform, data pipeline. And if you have any feedback, any questions on that, feel free to ask me. So about us, we are Concur, now part of SAP. We got acquired by SAP, and we provide travel and expense management services to businesses. Your business might be using this. Any of you are using Spark Concur already here? Okay, nice. Okay, if you are not, you feel free to check us out, and you can try our solutions. And I work for the Data Insights team, and this team is building reporting solutions and providing customers access to the data. We do visualization. And we also provide the customers API access to the data. So data is primarily all we do. And here is the stack so far. We love ETL. And we do a lot of ETL. And we generate all this data through our application front ends. And we store them in OLTP backends, like any other application do. And then we do ETLs, and then we produce OLAP databases. And we do ETL at a higher scale. We have about 28,000 ETL jobs, which runs per night. And I'll be presenting some other numbers as well. So, and the number of OLTP databases we have is around 7,000. We have a mix of single-tenant and multi-tenant databases, which stores data of customers, and then we create individual databases for each customer for OLAP and reporting. So in that sense, we have about 7,000 OLTP databases, as I said, and 14,000 OLAP reporting databases, and we run 2 jobs per customer, which is around 28,000 ETL jobs that we run. And we process about 300 million rows every night, which has been compacted. And the total number of estimated change over the day is around 202 billion rows.
Can you turn it down a little bit so you don't get the feedback all the time?
Sorry about that. Is it any better now? Oh, good. Any better?
Well, if you walk around and we get feedback, we'll let you know.
Okay, thank you.
That should be obvious.
Okay, so the good thing is that we have about less than 20 failures a night, and most of the failures are because constraint violations or sometimes foreign key reference or integrated failures and things like that. Maybe I'll just move close to the monitor and then start. Right.
Hey Santosh, just
Yep.
turn down the volume on that.
I don't know how to do that.
The volume. Either that or the speakers, because that's how it's feedback. It's
Yeah.
nothing to do with your mic position.
Yeah. I'll try to speak without this probably. Did you raise the volume down? Okay, now it's better. So here are some of the traditional batch ETL challenges. So they are scheduled. They are scheduled to run at different times of the day. Most of the jobs run overnight. And there's a high latency, because by the time you get to run the job, you're already delayed by 24 hours or whatever time that you schedule the jobs to run them. And there's a higher processing time, because now you get to process a lot of data at the same time. And I'll be talking about some of our problems next to this. And they're hard to scale, because traditional ETLs, either it is you're using an ETL tool like Informatica or something like that, or if you have built a custom one, they are hard to scale because you are logics on top of logic, and then becomes complicated to maintain, and they're hard to scale because they typically run on a single node. Right, so, and they are not fault tolerant most of the time, unless you have built any custom logic around it to make them fault tolerant. And they're monolithic, as I said. One single ETL job basically does extraction, transformation, and loading the data. And there's a higher maintenance cost, especially in a use case like ours, where you're running too many ETL jobs, and then you have to monitor them. There is a higher maintenance cost. And every time there's a failure, going back to the original state, and then recovering from there, it becomes a challenge. So we thought about solving all these problems, and we came up with some of the tools that I'm going to talk about in going forward. As I said, because we are processing them in a scheduled fashion, most of our jobs run until midnight, and has high dependency on other different job chains. Once they finish, this job kicks off, and then we get to process all the data, but at the same time, and we do not finish processing all our data that we wanted to process. So some of the jobs finish really fast, like they finish under 1 hour, and some of the jobs, they hang on there and run for longer duration, like 6 hours. So by the morning, so we have a commitment to make our data available to our customers in the morning, and we cannot get to that because now the job takes more time than that. So this is what we're thinking going forward. So moving forward, so from scheduled, we're going to make it more streaming and more real time. It's a micro batching, is that what we need? We do not need row basis real time, like every time a row changes, we do not have to process them, we can do micro batching. From scalability wise, we have to make the solution a little more scalable. It has to scale. If you have to process higher volume of the data, you'll be able to add more nodes into this, and systems should be able to scale automatically from there. And it has to be modular. So if you need to add a new transformation logic, your existing transformation should not be impacted because of that. And then it has to be fault tolerant, because if any job fails, the job should automatically restart and recover from the failure if node fails, because anything fails. Your hard drive could fail, your processor could fail, your memory, there are hardware failures, there are software failures, there could be many different kinds of failures. There should be a redundancy available to pick up the fault if there is a fault. And in order to do that, the way we're thinking is that, so our existing system is ACID compliant. Everything goes through transactions, and the data that we store is very, very highly normalized. It is traditionally designed, so no surprises there. It is normalized. So going forward, we're making it more eventual consistent. So the data will be consistent at any point of time, but it is not going to be consistent with the OLTP system as it is. And reducing the maintenance cost is another aspect of this design process. Because now, we have about 28,000 databases. It is constantly growing, and we are constantly adding more customers. Down the line, maybe after a year, we'll have a lot more number of databases to maintain, which is already problematic already, and we want to solve that problem as well. So we are going to build a streaming data pipeline in order to do this. And now we know that, so now we're going to build a streaming data pipeline. Let's take a look at what are the solutions out there in order to do it. What are the tools that we're going to need, what are the choices we have, and what we're going to pick. So first thing that we need to identify is where the data is coming from, what are the sources. This problem applies to any of your applications also. I mean, when we start streaming processing, identifying the source is very important, because where you're going to get the streaming data. And typically, the database, here are some of the sources. I mean, this may not be applicable. This may not be related to our scenario, but your data might be coming from the applications. The applications are constantly generating data from the user interactions, or there are mobile devices. They're generating events, or there are sensors, and there are lots of Internet of Things devices that are coming up. They are also generating events that can be used as data sources. And in the worst case, this is kind of a fallback scenario. So If you already have databases which are writing their data to the write-ahead log or the transaction logs, you can do database log scraping, and you can still generate streaming data from that without modifying any of your applications. But this requires an operational involvement because you need to install additional components on your databases, depending on what database you are using. There are database-specific solutions available. It might be your last resort to go. But if you can generate those events from your applications, that will be your first choice. And this is our first choice in our case. And then we're going to need a flow manager. This is basically a flow manager and a control aspect because when you get the data, you might not be able to process them in real time. There might be a backlog, back pressure built in when your data is getting processed. You need to have a flow manager to control the flow of the events from your source to the processor. The processor is going to come next. And I'll talk about what different flow managers are available today. So you have traditional message queues, RabbitMQ, ActiveMQ. There are many different message queues. You can use any of them. Kafka is a great solution. Kafka is traditionally designed for kind of handling high volume streaming data. Flume, some people use this to capture all the logs files and transfer them to a streaming processor. You can use Azure Event Hub. Event Hub is designed, a scalable solution which is designed for storing all these events. Kinesis is another one, like Azure. There is SDFS. Some people store that streaming data into SDFS and then do process on top of it. And then the third thing that you're going to need is a streaming processor. And here are various choices. Storm is one of the most popular streaming processor out there. Storm is a great one. It was designed at Backttype and got acquired by Twitter, and Twitter uses this for trend analysis. This is a little hard to write code in Storm, and you have to understand the Storm model really well. And it does by row processing. So every time, event by event processing. So every time a new event comes in, there will be Sparks kicking in, and there are bolts which are going to process that event. And Spark streaming is kind of a little different than that. Spark streaming does in a micro batch fashion. It waits for a certain duration for all the events to come in, and then aggregates them in something called D streams. I'll be talking more in details about that. So D streams are generated and then does any regular transformation on top of that, and you can store the data into any storage solution, or you can generate alerts from there, or do anything on that. And there is another one called Azure Stream Analytics. Azure Stream Analytics basically provides similar functionality, but if you are storing the data on Azure already, you can process them in real time using Azure Stream Analytics. I'm not sure if AWS has got a solution, but there are other solutions like Samza and Flinks that can be also used on AWS as well. So once you process the stream data in a streaming processor, you can do two things. You can do file alerts, and if you are interested about learning what different patterns going on, and if you want to, one of the examples is a fraud identification. So if you're looking for frauds on your transactions, you could be alerted anytime in a real-time manner, every time there is a fraud happening, instead of waiting for the midnight when your batch job kicks in, and then you do the processing and you identify the fraud. So you can identify fraud in real time, which is one of the great use cases. Or you can store the data in a storage solution, and you can still do reporting on it for long-time reporting. And you can use any kind of analytical storage. Columnar storage are typically used for this, but your regular RDMS will work. NoSQL are great for this because they're more scalable. SDFS is a great solution for long-term archival storage, and you can use a warehouse solution like Amazon Redshift, or if you already have a warehouse, you can leverage that for storing all the streaming data, which is after processed through the streaming processor. And then you do reporting on it. It's a traditional, this is your intention. This is your outcome of your processing all the streaming data. And you can write a custom app to do reporting, or you can use Tableau, Excel, Cognos, anything. You can use it with that. Any questions so far? Okay. So let's talk about particularly Spark streaming, and we picked up Spark streaming as a solution for us. As I said, micro batching works best for us, and 95% of the use cases can be satisfied with micro batching, unless you need real-time processing, which is like near real-time processing. Spark streaming does great on that. Spark streaming is one of the components of the Spark family. So Spark has all these kind of components: Spark SQL, Spark streaming, Spark machine learning, and there is a graph processing which is called GraphX. all this runs on the Spark Core APIs. Spark Core API provides you the transformation logic, like you can do join with a different data set. And these Spark data sets are distributed and they run on multiple nodes. You can partition them and you can run them on multiple nodes. They're fault tolerant, and Spark streaming is great at fault tolerance. I'll talk more about that in the deep dive of Spark streaming after the demo. And as I said, this is fault tolerant, and this is part of Spark for processing real-time streaming data. And this is one of the questions that we asked ourselves, and this is a few times being asked by my team itself, is that why Spark? Why not Storm, or why not something else? So one of the key benefits of Spark itself is that Spark provides both. Spark does batching. You can also use Spark for streaming. You can also leverage Spark SQL for SQL-like queries on your existing data, and your data could be stored in SDFS, it could be coming from different OLTP sources, and you can combine, aggregate, and join them all together and get the data from Spark SQL. So if you have written one logic in Spark streaming, you can reuse that for Spark batch as well. All your existing investments can also run as part of batch. So because we're not 100% getting rid of streaming, also getting rid of batch, we still have some data coming in a flat file format in the midnight. We still need to do processing on top of those. We're still doing some part of processing in the form of batch, so we can reuse some of the logic that you would write as part of real-time processing. And I'll bring up the demo really fast, and I'll show you a real demo. It's not a real application, it's kind of a fake mock of the real Spark streaming application, where a producer is basically, or where it's a simulation of application which is going to generate streaming data really fast. And I'm going to put the data into Kafka, and from Kafka I'm going to process that, and I'll show you that in a demo really quick. So it's a single cluster, single node cluster of Spark. It has Hadoop SDFS installed in this, and you can see that Kafka is already there, and this is Zookeeper running on that. So what I'm going to do is I'm going to start a fake producer, which is going to produce data really fast, and before that I'll start a monitor, which is basically monitoring all the events that are getting into the Kafka, and I'll do this. I'll start the monitoring. So it is trying to create a new topic in Kafka, which is called expense report. It is already there, so that's why I got the exception. I created that before the demo to make sure that the demo works when I make the demo. And I've created 10 partitions in the Kafka topic. I'll talk more about Kafka later on this. And I'll run this producer, which is going to generate all these events. We're going to put them into the Kafka topic, and we can see them appearing in the monitor on the left-hand side. Okay, so this producer has a timer running inside it, so which is generating some random data. So that's why you're seeing the sequence of CSVs basically scrolling there. So I'm serializing my data in a CSV format. Just going into Kafka. On the right-hand side, I'll start my Spark job. I'll deep dive into the Spark job. I'll explain how the Spark job is written, how it's going to run. I have a detailed architecture of this, but let's see the demo first. And I'll start the Spark job. So the Spark job is doing two things. It's doing some filtering, and also it is doing a little bit of alerting. And it's a fake alerting. So assume so consider that. So expense reports are being submitted in real time, and all you're seeing on the left-hand side is some information about all the expense reports that are being submitted. And on the right-hand side, so the Spark job is processing the data and identifying a fraud. And in this example, a fraud is an expense report being submitted, which has a total value of greater than 50,000, let's say. And a little more than that. So I'll show you the example. So I've written a little reporting app, which will show the progress in real time, how many expense reports are being submitted at this time. Oh, did you see this alert? this alert is basically identifying one of these transactions that has identified which has a total amount more than 50,000. And this is all happening in real time. And I'll explain how this web application is going to push that. This application is written in Node.js, which is basically listening to a Redis instance for PubSub. And the Spark streaming, when it is processing the data, when it is doing the filtering, after it completes the filtering, it pushes that event to the PubSub of Redis instance. And this Node.js application is listening from the PubSub from Redis, and is picking up all the data and is using the HTML5 notification API to display this notification. But you could do like send text messages, emails, or whatever you like. You can integrate with the existing systems for alerting. And you can see that this graph is now showing a little bit of progress. It's showing how many messages it is processing. It is around 5,000 messages processing for every 5 seconds, I guess. Also the code, and the duration is configurable. Also, I think I specified for 15 seconds or something. So every 15 seconds, it is starting to process all these applications. It's counting how many expense reports are being submitted. But let's see what the application is about. So in this application, so I submitted the application. You saw me submitting the application on the right-hand side. So when I submitted the application was submitted. It's an application which was written in Scala. You can write Spark streaming applications in any of your favorite languages. Like you can write it in Python, you can write it in Java, you can write it in, now you can write it in R, and you can submit that application from a driver. The machine from which I submitted this application is called a driver machine, and the driver machine is kind of the machine which kicks off the job, and it stays there. It runs there until you kill the job, or something happens to the job and the job kills itself. And then you can have the driver launched in 2 different modes. So one of the way you can launch the driver, you can launch it from your laptop. Or you can submit this application to a cluster and identify one of the machines from the cluster as your driver. So you can submit a job and go home, come back, your job will still be running from there. You will not typically be submitting it from your application, but from your laptop, but it's a good way to build prototypes and development. And once the application was submitted, it was submitted to a master. It's a traditional Spark cluster setup. It has a master node. I'm using a standalone cluster in this case. You can run your cluster on YAML, you can run your cluster on Mesos. In this case, in any cases, there will be a master, and the master is submitting the application to different workers. And each of these workers are going to create an executor for each individual job that you submit. So if you're submitting 5 jobs, there will be, if you have 5 workers, you will have each of this worker getting an executor. And once the executors are created, the executor in typical, in a typical streaming application, your worker would create something called a receiver. And the receiver is the primary component. It's kind of a special kind of task. Let this finish. Okay, going back a little bit. So every time you submit a Spark streaming application, the streaming application will run as a long-running application. So there are two short-living applications, like batch applications. Once you submit, once the job is finished, it will be killed off. But if you're submitting a streaming application,
Sorry, Santosh. Sorry.
no problem. Okay, so I was talking about the receivers. So once this application is submitted, it will run as a long-running application on your Spark cluster. And all these workers which are running all these applications, all your tasks, and some of them will start a special kind of task which is called receiver. And the receiver's job is to receive the data from your sources. If you are familiar with Strong, it's kind of a spout. You can consider it as a spout, which will basically is going to listen to all these events. It can be your RabbitMQ message queue, or it could be your Kafka instance, where it is running the receiving the messages from. So once it has received the messages, it will create something called a D stream. A D stream has a collection of something called RDDs again. So RDDs are core concept of Spark core, and these RDDs are virtualized data sets you can think about, which is distributed across machines and stored in the memory. And when you do processing, unlike YARN or Hadoop processing, there is no I/O involved to the disk. So everything is in memory. It is really fast. It has a really good optimizer which is built into Spark. It'll skip some of the tasks that you're going to even specify, and it'll process the job really fast. And once you have the D streams, the D stream will be distributed across different nodes and will also be replicated. So the same copy of the RDDs will be copied across into a different node. Even though the node is not going to process it, it will still be there. And a task will be kicked off to process the data, and then you can, from the task, you can define whatever Spark activities that you want to do. Like you want to join with a different data store. And let's say you want to join with the historical data. If you're running a machine learning pipeline, you want to get some modeling data, and you want to load into the memory, and you want to do some additional modeling processing inside your task. You can do any kind of task in this. You can, in my example, I'm in this task, I'm writing to the Redis. You can write to a backend data store like your data warehouse. You can write it to the RDBMS. You can write to anything. And if one of this worker node fails, there will be because there are already executors sitting idle there. So one of this executor will just pick up the task and will continue to process that. So that is the built-in fault tolerance inside Spark. So if your messages will not be lost because they are written to a write-ahead log. So as soon as so let's assume that you're writing to a network socket. So you can use a network socket stream. Really? Okay. So you can write, if you're writing to a network socket and your producers are firing messages to the socket, and this write-ahead log is going to take all these messages, going to write to the write-ahead log, which is going to write to the disk or HDFS. So in case of a failure, it will read all the data from HDFS or from the disk. It will replay that on a different node. And in addition to that, so there has been some improvements starting with Spark 1.2. There is a tighter integration with Kafka. So you will need this write-ahead log because Kafka is durable itself. Kafka does a very good job at persistence because Kafka stores every message into the disk. So you're not going to need the write-ahead log. So that is one thing that this diagram doesn't have. It's called checkpointing. So checkpointing is an important factor which is built into the Spark streaming itself. So periodically, Spark will write some information to the disk. So it could be stages of your processing, some additional metadata about the processing, the stages of your job flow. It could be anything. So Spark does write all the data to the disk. And in case of a failure, it will read the information from the disk. But if you're reading from a Kafka source, which already has a copy of the data persisted on the disk, along with the memory, it will not try to write any information about the data to the write-ahead log or to the checkpointing, but it will store only the pointer, right? So it will store only the reference of the data as how far it has read so far. So if a job fails, the job will start in a different node, or maybe on the same node. It is restarted, and it will start reading from the same object, which is called in Kafka, which is the pointer it has last read from. So that way, Spark is somewhat being able to process the data in a fashion which is called once at a time. Guaranteed once or something. Exactly once, right? That's right. It's exactly once. It's not going to be exactly once. You still have to make all your processes, all your operations idempotent, but still, it does somewhat do exactly once kind of processing, although it is guaranteed to be at least once processing. So going forward from here, this is exactly what I was talking about. So previously, you would read from Kafka, and then you would write to the write-head log, and you will also store that in the checkpointing. But you don't have to do that anymore. Your driver can read the option from Kafka. Yes.
I'm sorry, I'm not catching that term, WAL. The what log?
Write-ahead log. It's kind of a transaction log.
Oh, I'm sorry, thank you. Okay.
It's kind of a transaction log that you write as part of the database. So you don't have to do this. This is much faster compared to the previous one.
So, in the at least once, does that mean that if I write if I've got a process that, say, takes a record and splits into two, writes it into two records,
Yes.
I have to make sure somebody else hasn't already done that?
And you don't have to.
You don't have to make sure yourself. Spark Streaming automatically does it. So it processes at one node until the node fails.
Okay.
So if the node fails, the data will start a different job and a different node, and it will start processing the same data. So in that scenario, you might have a duplicate record, but you have to make your processes handle that.
Okay, so you effectively have exactly one step, as far as I'm
Effectively,
writing
yes.
my code?
Yeah. So that comes with some challenges. So one of the biggest challenges with this approach is that you can't parallelize your data as much as you want. That means even if you are adding more nodes, you'll eventually realize that your data is being processed only a few set of nodes. Why it can't take benefit of all the nodes that you have, all these workers sitting idle there, but they're not doing any processing, because the number of partitions that you have in Kafka. It's the number of partitions you have in Kafka, those are the number of workers that will work. Unless you do some special work to partition it further after reading from Kafka. So same thing applies to Kinesis also, any source which supports partitioning. And there is a pretty good blog post that that is posted on Databricks, how they're, what are the changes. This article talks more about how they have made a change, or what benefits it's going to bring. And also, if you are transitioning from the older mode to the newer mode, what code change that you have to make in order to take benefit of this newer model. And now the time for our architecture. This is how our solution looks like, and this is how it's going to look like in the future probably. So service bus. So there will be a company-wide service bus where all the applications that Concur is going to write events to. So along with writing to the databases, the applications are going to be responsible for writing events to the centralized event service bus. So all our microservices are going to pick up events based on what are the events the microservice is interested in. So instead of applications pushing directly to the microservices are going to reactively read the data from the service bus. And here are the applications which stores all the data in their OLTP databases. And then we have different sources called travel tracks, where the data comes in a different transport mechanism in FTP, HTTP, and SMTP transports. They acquire all these flat files, and all these flat files need to be processed in the system as well. So we store all these flat files as a source into HDFS for long-term archival and processing, batch processing on that. And then our producer is basically going to listen to the events from the service bus and going to talk to the databases over the APIs or through SQL layer, and figure out the rest of the data that our stream process is going to require to process all the data. And then it's going to write to the flow control system, which is going to be Kafka in our case. And it's going to write them, serialize them, and store it in the Kafka. And our stream processor, which is going to be Spark Streaming in this case, Spark Streaming would process the data and then store it into the OLAP database. And all these OLAP databases will be distributed and replicated for failover and load balancing. And then our reporting solution will read from there. And in addition to that, so because we are storing the data in SDFS, we can normalize the data before processing in the SDFS itself, and we can do that through a Spark batch. And we can transform them and normalize them before fitting into the Spark. And the Spark would process all the data and will combine the data that is getting in the real time. And also, because now we are storing the data in SDFS, that gives us an infinite scalability to store and process all the data, right? So SDFS is massively scalable, but it comes with a cost of latency, right? So you can only read from SDFS in a batch format. There is no real-time access to that unless you do a caching backend like Tachyon. So Tachyon basically is a backend for SDFS or any backend like S3. So your storage, so every time you try to access the data, the data would go through a layer, and it will get cached in the memory. And depending on how much memory you can provide to it, it will just do the caching. And every time you try to access the data will be faster. And it doesn't have to go through the name node, data nodes, and doesn't have to figuring out. Yes?
So I'm a little bit confused. The previous architecture, you had OLTP part and then OLAP part.
Yeah.
But here you still have OLAP part. And you mentioned previously, and it's true that OLAP is not scalable in
Yes.
terms of failover, etc. But here you say, hey, load balance failover for OLAP.
Yeah, so this architecture that we're building, we're making it future-proof. So the reason we still have the OLAP is that some of our reporting solutions still need a SQL access to the data. We have done an abstraction. I'll talk a little more about it because this is not a complete architecture yet. So we have a Spark SQL layer, which is basically going to talk to the, it's already there. So you can see the Spark SQL layer, which is going to talk to the SDFS to get the data in a SQL format. But some of the proprietary reporting systems that we have, they are not Spark SQL compliant yet, because Spark SQL is not ANSI SQL compliant yet. And these systems need to have ANSI SQL compliant sources to read the data from. And until that happens, we'll still be reading the data from the OLAP system. And there is nothing wrong in storing the data in the OLAP, as long as we can move some of our historical data to SDFS and do only the real-time data into the OLAP systems. So that way it is kind of partitioned. So your historical data goes to SDFS, and your current view stays in the SQL systems.
For the SQL requirements for your reporting, proprietary reporting tools, why are you using Spark SQL and not like a Impala, JDBC, ODBC?
Yes, so we have started experimenting with different solutions like that. So there is the Apache Drill, which is more SQL compliant than this. We're also experimenting with that. But the systems that we have, so Apache Drill and Spark SQL, they both are still batch oriented. So there is a little latency that in order to get to the data. Whereas it is always faster to go to the OLAP system. So if you are looking for a data which is like yesterday's data, you can always get it faster if you go through the OLAP layer versus going through that layer. So it is kind of a faster route to get there. But all your data, after being processed from the Spark streaming, is also available in SDFS. So what we can do is, so we are trying to do this trade balancing. Whereas if there is a job which takes longer to run, like a reporting job which takes longer to run, we'll offload them to SDFS, versus the jobs which are typically expected to run really fast can be run on the SQL. So it's kind of redundancy built in. So if you get it off totally the SQL layer, the OLAP SQL layer altogether, the system will still survive. And that's our long term. So until we find a real SQL replacement for SQL on SDFS. It's kind of a hack. Yes?
What is the producer here? Like, what is it written in? And
Good question. I mean, the producer is basically, it's kind of another application sitting in the middle, which is listening for the events. The reason we have it is the service bus, the centralized service bus that we're going to have, the service bus is not going to have the entire data available as part of it. So the producer is kind of, it does joining of the data that is available in the event, the service hub, and will get additional data from the APIs.
why can't streaming can pick that up?
So the reason we have it is we do not have the service bus yet in the system. So it is kind of an abstraction that we're trying to build. If we need to change a component, we can change the producer without having to change any of our transformation code. So our transformation code will remain the same, irrespective of whether we have this producer listening from service bus, or doing a database log scraping, or doing something else. So right now our approach is doing a database log scraping, but eventually we're going to this route where we're going to be listening from service bus.
So these custom Ps there that are producing JSON for the broker
Yeah.
would be replaced by this general purpose service bus that consume the events and made them into whatever, sending them to the right broker
Right.
and whatever.
Right.
But right now you've got a pile of different Ps consuming whichever source.
Yes, that's right.
Is service bus also based on Kafka, or?
The service bus would also be based on Kafka. So yeah, so I think once the service bus is there in place, we can replace that producer. Even we can replace the producer altogether, because we can use Kafka to Kafka replication in that case sense, depending on how much data will be available. Because we are still determining company-wide, what will be the standard for storing the data in the service bus? Because some people are proponent of storing a reference only there. Like you just store the reference, and if you need to get additional data, go use the API to get the data from the data source.
Do Spark and STFS reside on the same cluster?
Do Spark and STFS reside on the same cluster? They do not have to, but yes, in our case, it probably will.
How do you control the memory allocation and things like that, so that STFS jobs are not affected?
Okay, so SDFS is a separate component. So I think I answered it wrong. So Yarn and Spark are going to run the same machine. SDFS, we have separate set of cluster for separately for SDFS.
I meant Yarn.
Yeah.
Yarn with.
So we won't have any Yarn jobs going forward. So it will all Spark. So we are going to change all our Yarn jobs. We don't have any Yarn jobs, to be honest with you, right now.
So inserting into Kafka, this is at least once semantic. Like, how did you overcome that problem? Do you need like exactly once inserting to Kafka as well? Like I know that.
No, we don't. We're going to expect duplicates coming in.
Oh, okay.
So we're going to make our processing layer idempotent so that even if there's a duplicate record coming in, it will just produce the same result.
And you're okay even if the duplicates are after, like they're not in order. You're fine with that.
We are okay with out-of-order processing. Yes, and that is one thing we're experimenting right now, figuring out how to handle that. Yeah. So,
yes, I think one thing you talk about, you have like 28 job or something. You didn't use Yarn, and I know standalone cluster you have to one finish you start another. The Yarn you can share, but how do you put it in one process? Then how do you schedule and connect jobs?
that's a great question. So actually, we don't have Yarn yet. We don't have any Yarn jobs. We do have Yarn as part of the cloud offering because we just created the SDFS right now. So what we're going to do is we're planning to use a standalone cluster. And standalone cluster is the same as running on Yarn or Mesos because the resource allocation basically happens by a Spark scheduler instead of using a Yarn scheduler. So the way we're going to have it is kind of a statically allocated. You're defining each worker is going to get like 512 megabyte of memory, or depending on what the configuration will look like. It's not dynamic, to be specific to your question.
What was the design rationale for having Tachyon in there?
Faster access to the SDFS data. Yeah, because in the long term, probably we'll just get rid of this OLAP system altogether. We'll always go to the SDFS for getting the data, and accessing it to SDFS, any data is kind of painfully slower, right? All our reporting system cannot afford that latency to wait for SDFS to get all the data from different data nodes. So Tachyon is going to be our caching layer for that.
So if HDFS provided you a faster access to data, both read and write,
yes,
let's assume, then you can get rid of your service bus, your Kafka, your OLAP, everything in this picture. Is that true statement?
It is not. Service bus cannot be got rid of because service bus is something which is all the applications are going to write to.
Right? So they can write to HDFS directly, right?
They won't. They are not dependent on HDFS because not all the application needs access to the HDFS libraries or anything.
Right.
But they can, yes.
They can.
They can. Technically they can.
Yeah, if HDFS provided you that faster read-write
Yes,
access,
yeah.
you can get rid of your service bus, Kafka, OLAP. It will be much
Absolutely.
more simpler for you to run the whole system.
Yeah, if it is there. But it is not, unfortunately.
I have one question.
Yes.
What will be necessary to get rid of the OLAP? Is it possible to get rid of the OLAP there?
It is totally possible. If you're writing a custom application for the reporting, probably we can. But we have a legacy system that we still need to support for the reporting, and that requires ANSYS Eco compliance data source. So we cannot get rid of that right now. But eventually we will.
So it's more data coming from other places that is also being combined there.
Yes. So I think that there was a layer where it was Spark SQL was sitting between the OLAP and the HDFS, but I intentionally moved it out because it is not there in the picture right now. So it will be the fashion for accessing any kind of SQL data. Yes.
What kind of monitoring do you have in place for your Spark cluster in this jobs, specific, the hardware and the jobs?
So monitoring wise, we haven't figured out that operational stuff yet. So we'll figure that out. So we'll use any regular Spark monitoring service. Yes.
Actually, I mean, having the OLAP with real time, how often do you process OLAP? Because OLAP, I mean,
So right now, probably everything is going to the OLAP. Eventually, everything will go to HDFS. So at some point, there will be a balance between both. So all our historical data, let's say data about 5-year-old will go to HDFS, anything newer will go to the OLAP.
What's the latency there? What's your SLA to the client for the OLAP?
So we have some kind of reports. So it's dependent on the reports. So some of the reports are scheduled. So let's say you want to get this report by the morning. So we know that it can be processed in the batch. Even if it takes like 20 minutes, that's okay. But if you're running a report in ad hoc manner, you're coming to the system, you're running your report to see the results, you probably go to the OLAP. It's faster that way. But with the caching layer, I don't think that will matter that much, but depends.
Can you talk a little bit more about your decision to run without Yarn and just use a standalone resource management, or is it just simpler for you?
It's much simpler because we're not going to have any Yarn jobs. I think it makes sense when you have Yarn jobs mixed with Spark jobs, and you have a very unpredicted workload that's coming. It makes sense to run Yarn, or even Mesos does an even better job in that, but we don't have any unpredicted workload that we are probably looking at. So it's more predicted. We know how many customers we have to support. Yes.
Okay, so basically you replace 28,000 ETL processes with some sandwich trees log files and send them to the same OLAP system.
Yes.
And instead of night time, you do it throughout the day.
Yes.
So really, ETL was a bottleneck?
So the latency was the bottleneck. We're still doing ETL. So I think the Spark is all it is doing is ETL. It's doing the transformation. So we are extracting data with a different process and transforming and loading them. So we're still doing the ETL. But we're doing ETL in a newer manner, in a newer fashion.
In the Spark step, when your T is down, I mean, there's still the steps there, but it's all in the Spark. I mean, well, the first part is in the P, but
Yes. So the P is basically extractor, and the transformation is happening at the Spark layer, and the load is happening into the OLAP from the Spark layer itself.
I see that you have Hive/Spark SQL there.
Yes.
Have you considered Hive QL use cases versus Spark SQL use cases, or have you considered performance differences between both?
That's a great question. Actually, the reason I have Hive over there is, so Spark SQL is a Hive SQL. So underlying, it's a Hive parser. So any reporting system that can speak the Hive language, Hive QL, will be compliant with the Spark SQL. So we're not planning to use Hive. We're planning to use Spark SQL.
You're just using a Hive context.
Hive context, yes. Yes. Spark SQL context is kind of abstraction of Hive SQL context anyways. It's the same thing.
There's some difference. In fact, I log about Spark SQL, just the parser they implement. They say is a toy parser that in fact it has thread deadlock issue.
So yes, that is the implementation details. But they have basically taken the Hive parser and implemented that inside Spark SQL. It's the same parser. So parser-wise, it is the same. But the underlying implementation is different.
Hey Santosh, I just want to make sure that you have time to finish the
Okay.
rest of your presentation.
Yeah,
So
I
if
think-
everyone can hold the rest of the questions till the end, then
I think this was my last slide. There's a little more. So we are still planning to do some sort of batch, because we still have some sort of data that is coming in a batch format. So we're going to do some extract compensation process in the batch format, and we'll be processing them through the same transformation logic that we probably will write. And that's the core reason why we're selecting Spark over any other streaming processes that we have. And also, this enables us to provide API access to the data that we have. Previously, we were afraid about scalability ourselves, so we couldn't enable API access to our customers. So this enables endless possibility for our customers who can get API access to the data, and they can build reporting solutions there themselves. I mean, they can build their applications, we're going to consume the data from our systems without us having to worry about the system scalability, because this system is going to scale infinitely, literally. So I think with that, so this is my last slide. Will Spark Streaming survive the Chaos Monkey? So this was an experiment done at Netflix, where they have tried to run Chaos Monkey on the Spark cluster, and they have identified the back pressure building at different places, worker failures, master failures, your driver failures, And this is a simulation of that, so that URL, I'm posting this slide afterwards. So you can read this article. It's a really interesting article with the experiment that they did with Spark streaming. So with this, I think the one thing which really stands out is the driver failure has a major cost compared to any other failures. So you want to run your driver as part of your cluster instead of running that as part of a laptop or maybe a workstation. So that was my last slide. There was one slide I intentionally skipped, which is a discussion about Kafka. So Kafka is an actual choice for us because of the tighter integration with Spark. And it is also, it does one thing right, which is persisting the data in a durable fashion. And also it is partition tolerant. So if you can lose partitions, you can specify a number of replications when you're creating a topic in Kafka. And Kafka has the best class integration with Spark, so that's the reason we are also going with Kafka. So with that, that's my last slide. Any questions that I can answer? Yes.
Can you talk about how you specify the stream partitioning?
How do you specify the stream partitioning? It is partitioning at the producer level. So Kafka expects the producer to partition the data and determine which partition to write to. Otherwise, you'll just take the default partition, which is kind of a round-robin manner.
Okay. You don't partition once it comes into stream?
No, we don't have to, because it is already partitioned when it is stored in the Kafka topics.
Okay.
You talked about providing API access to the data.
Yeah.
How do you plan to achieve that?
With the current system, I mean, with the newer system, you mean?
Yeah.
So now, with the API, so it will be REST API. I mean, are you asking about the protocol? It will be REST API to the customer.
Okay.
With what authentication on top. That is our company standard, so to expose the data to customers.
So I think we have time for one more question, and then we have to move on to the next presentation.
Have you looked at Flink or other things instead of Spark streaming?
Yes, I personally am not a part of this exercise, but I personally have looked into Flink, and in fact, I have written an article on Quora comparing both of these systems, like Spark and Flink. So we found that the community is bigger. The reason why we wanted to go with Spark, there's a bigger community around Spark, and lots of people are using Spark. So versus there are only a few companies who are starting to evaluate Flink. So the decision was natural.
So it's faster, right? Like Flink is not micro-batching, so...
Flink is not micro-batching. It's an alternative comparison to Storm, but our use case is more micro-batching. We can run our batch job more times during the day, which will essentially give us the same as micro-batching. That's what we want to do.
Can you get a big round of applause? We have Anikate and Stephen from the Data Sciences and Services team, and they're going to talk about a prototype they were creating using Spark streaming as well.
Can you hear me? With all the excitement with Spark streaming, the data science team actually wanted to try out Spark streaming, and as part of the learning curve, we decided that we'll come up with a use case ourselves to try it out. So this is actually an experimental POC we did. Some nice, interesting learnings we had, and the purpose here is today to just quickly share some of what we learned during our experience with Spark streaming. So essentially this use case is about, essentially it's queuing theory actually. So the use case here is that there are a bunch of tasks coming into a queue, and some proportion of those tasks need to be routed to a service center where a human is actually going to review those tasks. The challenge here obviously is there are lots of parameters which you need to consider when you want to optimize this queue. That some of those parameters could be the queue length, It could be the capacity of your service center. Also, what sort of rules do you want to apply on those tasks when you want to flag those tasks for reviews. So what we're trying to do here is dynamically flag transactions while they are passing through the queue to control their throughput for one. Also create a infrastructure service on which this is running so that it is decoupled when the task creation process is decoupled from the actual task flagging process. Real-time visibility on the task flow rates and the ability to perform some analytics on that. So essentially in this, what we wanted to do is that along with Spark streaming, we wanted to figure out how would we deploy a data acquisition and processing pipeline for doing this. So this particular slide essentially captures how we built that. So the first part, the top part of the slide, shows how we built this. Essentially, we are using Docker containers. We have small 5 applications, each of them encapsulated in their own Docker containers. The task producer essentially generates these tasks, and that gets posted to Kafka, to a topic or task. And then Spark streaming job is essentially reading of Kafka to get visibility into those tasks. Also, the Spark streaming job holds that logic of how do we flag those tasks, how many of those tasks need to be flagged and why. And that logic is encapsulated. Steve is going to talk about that bit there, about how Spark streaming is doing that. So once a bunch of those tasks get flagged, they get then consumed by a Java consumer, which then essentially, for the purpose of this application, just aggregates those tasks on a minute-by-minute basis, so that we can see, well, given a constant, say we have set a constant proportion of 0.75, so 75% of the transactions should get flagged in a random manner. So we want to basically be able to see that given the total number of transactions flowing through the system, how many of those are getting flagged in real time, ideally. So that's what this does. One more thing we try to do here is that, say somebody is monitoring the system and he can clearly see that this system is overloaded and they want that the flow rate should be throttled off. So is there a way, can they intervene and provide some sort of an input into the system so that this pipeline can throttle the rate at which the transactions are getting flagged for review? So that's why there is a third topic here called overload, and then when you post events to that overload topic, it essentially, the Spark streaming job, which was previously just flagging tasks, is now going to dynamically modify the proportion or the proportion rate at which it was flagging those transactions before, and essentially that gives you that dynamic capability of actually intervening in a real-time manner in this flow rate to throttle it. Well, just before Steve dives into the Spark streaming aspect of this and explains what challenges he faced, what he learned, I'll quickly show you the application itself. So this is the real-time dashboard here. Unfortunately, my Mac is, I'll show you this different one. Okay. So this is the real-time dashboard here. And what you see, the black line is the total volume of transactions flowing through the system, and the blue line is the percentage or the volume of transactions which have been flagged. As I mentioned at startup, the Spark streaming job is actually sets the proportion to a constant value. So ideally, you would see that these two lines should go along together in the same proportion. But you will see that's not always the case. So there are two reasons. One reason is the random sampling methodology in Spark streaming we used, which kind of which is because of which actually you don't see it maintaining that proportion. The second reason is a couple of times during the runtime I actually hit the panic button. And so when I hit the panic button, Spark streaming job actually throttled back the number of transactions that were to be flagged, and that's why you see a huge dip here during which actually it was throttling it. So with that, I'll hand over to Steve, who will talk about the more interesting part of this presentation, which is the Spark streaming part.
Okay, so I'm gonna go through some stuff, but first off, I'm gonna give you an overview of what I'm gonna go through, and there's sort of three main points that I want to touch on here. First off is this flagging strategy. It's basically how we choose which tasks or transactions to flag. And there's two basic ways that we've chosen to do that in this demo. First one is a random sampling. Let's say you want to take 10% of your overall tasks and flag them. We can do that. We can also dynamically change that sampling rate, as Anikate said. Let's say somebody sees that it's overloaded and they want to dial down. They can press a button, and that will dynamically take down the rate, and then it'll come back up. I'll explain that in a second. The second way is to actually take a look at the tasks, the transactions, and say, hey, this transaction should be flagged because of some reason. And we can also dynamically change the reason. And I'll explain that. Both of to do dynamicness there, you need to maintain state somehow. And so I'll talk about that, how I chose to do that in our Spark streaming app. And then finally, I'll just touch a little bit on getting data in and out. Santosh did a pretty good job of talking about that kind of stuff, but I'll talk a little bit. Okay. So first off, flagging, random sampling. So we have a initial rate at which we want to sample our tasks. And let's just say that's 10%. And so whatever that rate is at any given time, we're going to go for each individual transaction, we're going to randomly choose to do that or not based on based on that rate. So technically speaking, all said and done, if you had a constant rate of 10%, you may not get 10% of transactions sampled, but that avoids having to keep track of how many you sample inside. But you can also change the rate, and we did. We have a panic button, we'll say, where somebody presses it, and when they press that, it'll drop down. It'll drop down to 90% of the previous rate. So let's say it's 10% at one point. Press that panic button, it goes down to 9%. If you press it multiple times, then it'll go down even more, but whatever. And then as soon as you press it, it starts going back up again, because we want it to be around whatever the target rate is. So and each micro batch that it's not at the target rate, it'll bump up a little bit, and it turns out in our demo app, it bumps up about 2% of the distance from its current rate to its target rate, each micro batch, which in our case was 5 seconds. So it'll slowly asymptotically rise back up to our target rate. Okay, and then down in the little box, I just have equations that represent how the rate is going to change depending on these two events. Okay, so the second sort of flagging is actually transaction analysis or task analysis. And so an example here would be outlier detection, fraud analysis. And let's say that we want to flag transactions that have some value associated with that transaction greater than 95 percentile of all the values of all those transactions. Now you can do that by doing a batch process before you start the app and coming up with what that quantile is, and then just using that as a constant. But you could also do it in another way, a kind of cool way. You could actually update the percentile based on the values of the transactions that are coming in. And a naive way of doing that would be to save all the transactions, and then at each micro batch, compute the percentile based on all that data. But that's going to be ugly, especially if you have a high volume streaming. So instead, what you can do is this cool trick called, you can basically create a form of binary tree, which represents basically the counts of the value within individual buckets. And the specific kind of tree that we're talking about is a Q tree. This is from Twitter's Algebra library in Scala, and it's related to a thing called a Q digest. Basically, all this means is that it's a tree that has a specific, where the nodes are split at specific intervals. And they're always going to be that way for a given system, such that you can add two trees together in a meaningful way. So then, for each microbatch, you can compute one of these trees for the transactions that you have in that tree, or in that microbatch, and then add it to the next one. Pretty cool. Okay, so both of these strategies depend on maintaining state. So you could maintain state in like outside of Spark. You could do it in a database. You could do it in. I considered doing it in sort of hacking Spark, and because Spark is built on Akka, you could hack in and send off to a remote Akka system to do this sort of stuff. That'd be kind of cool, but unrealistic. But Spark has a way of maintaining state within a Spark streaming app. And basically what you have is a dstream that's a key value dstream. And so you have the keys are, whatever you want, and then the value of those key value pairs is the current state. And each time, at each microbatch, you take the state of the previous microbatch and the data of the previous microbatch, and you use an update function, and it updates that. So it's actually like pretty simple, but it was complex to learn when I first taught myself. Okay, so this is sort of just a diagram of that process, and I'll show you. And you use a function that you define to update state, and I'll show you an example. So it takes two inputs, a sequence of values, which correspond to the value in the key value pair of that microbatch that you're looking at. And then you also take the previous state, if there is one. So you use a Scala option. And then based on whether you have a state for that key, you update it, or you create a new state, whatever. And then your new state is basically the return of this. So. Okay. Okay, so then let's talk a little bit about getting data in out. If you're using Kafka or one of the main receivers, pretty straightforward. You read the docs and pretty simple. If you want to get data out, if you want to put it into a database or if you want to put it back in Kafka, then you need to really create your own connections within the Spark streaming. And you got to watch where your code is run. So there's for a dstream, there's a method for each RDD. And that will basically, for each of the little mini batches, do something. But it turns out that method executes in the driver. So it doesn't get any benefit from the parallelization of Spark. But if within that, for each RDD, you do a for each partition, now you are executing on the executors, the non-driver. And then you can create a connection within that for each partition block, and then do whatever you want. So, yeah, that's that. Okay. Any questions?
We're using Kafka and partitioning it. We have write partitions meaning nothing is coming in this partition. And you have the number of processes set to the number of partitions you have in Kafka. How do you deal with it? Do you have inefficiently using your processors in that case?
Yeah, actually for our demo, we were totally inefficient. We only used one partition, and we ran it in Spark in a local node. So I guess we haven't dug deep enough into the Kafka integration with Spark Streaming to give you a good answer to that. Santosh probably could give you a better one.
Yeah, you can explicitly parallelize your RDDs once you receive the dstream and run them on different workers. So for example, if you have one partition, one Kafka, you receive it, and you're just executing on one worker, you can say parallelize it further. So it will distribute and work with different nodes. So different workers will just get engaged after you call the parallelize. So it's a hack. So it's not something which is built in, we should have built in the system to take advantage of that, but it's
In Kafka restriction.
Yeah, it's a Kafka restriction. I wouldn't say it's a Kafka restriction. It would be
Or your partitioning you can do.
partition mechanism.
Anything else?
Need a big round of applause for Anikate. So thanks everybody for coming tonight. Before you go, I just want to announce